Hello everyone, welcome. Today I'm going to give an introduction to our work, UFuzzer, lightweight detection of PHP-based unrestricted file upload vulnerabilities via static fuzzing co-analysis. My name is Junjie Zhang. I am an associate professor with the Department of Computer Science and Engineering at WRIGHT State University. This system is about the detection of unrestricted file upload vulnerabilities. This specific type of vulnerabilities is going to allow an attacker to upload a file with malicious content into a web server and later execute it. Here I have a quick demo of the exploitation of this vulnerability. For example, this web page expects the external user to submit a photo or image file. Instead of submitting the image, an attacker may submit an executable PHP file. And unfortunately, this web page is going to accept this PHP file, and later the attacker can directly access this PHP file. And this PHP file is going to be executed on this vulnerable server, and then the attacker can just feed different types of command and parameters. So this web server is going to execute this script with these commands and parameters and return sensitive information back to the attacker. So you can see this is a PHP scripts that has been submitted by this attacker. Here I'm going to give a little bit more technical background. On the left side, it is a client who is trying to upload a file to the server on the right side. So the client is going to establish a new session whose ID is called new file. Once this session is created, the server is going to maintain a super global variable files to store the information relevant to this session and the uploaded file. So the file super global variable is a two-dimensional array. The first dimension is indexed by the ID of this session, new file, and the second dimension is indexed by some predefined keywords. Okay, so here the client is trying to upload a file with the content and also the file name. And once this file is uploaded to the server is going to store the content of this uploaded file, but usually in a temporary directory, and also the server is going to assign a randomly generated file name to this uploaded file. Let's say in this case, the server is going to give XYZ to this uploaded file, and also it is going to keep this temporary file name, and also the server is going to keep the original file name into the file's super global variable. But this is not the end of this story, right? Because usually the developer is going to store this file in a more meaningful directory with a more meaningful name. So this action is usually done by an API that is called move uploaded file. So this API has two parameters. The first one is going to indicate the name of the temporary file, and the second one is going to be the name of the file to be stored. Well, you can see the second parameter should be sanitized, right? Because you do not want the name of the file to be stored is executable, right? For example, with an extension of .php. So this is one example that has this type of vulnerability. So you can see a variable is created to indicate the directory the developer wants to use to store the file. So it is contained in a variable that is called dir or directory. And then this script is going to evaluate whether this directory is writable or not. If that is the case, the specific file name is going to be created, fname. So this fname is a concatenation of the directory and the original name of the file uploaded, right? Because it is from the file's new file name, so that is the original name of the submission. And then this script is going to use the API move uploaded file And you can see the first parameter is going to indicate the name of the temporary file, and then the second parameter is the name of the file to be stored. This script is vulnerable because it directly uses the name of the uploaded file. So in this case, if the external user uses my.php as the original file name, so my.php is also going to be used as the name of the file stored in the server. So unrestricted file upload vulnerabilities represent one of the most significant threats against the Internet of Security. So it is very important for us to detect such vulnerabilities. A few years ago, we proposed a system called UChecker. UChecker leverages a static analysis to perform the detection. Essentially, it is going to model the exploitation conditions as symbolic constraints and use a SMT solver to assess the developed constraints. So this system is highly efficient. However, it introduces semantic gaps between the system under analysis and the vulnerability models, which is going to imply some inaccuracy in the detection. And specifically, you can see the original program is written in PHP, but the symbolic constraints are written in Z3. So which means that we have to find some rules to translate the APIs and operators in PHP into those in Z3, which is not always effective. Another approach that is called Fuzz leverages fuzzing approach completely, right? So it is going to run a web service and it is trying to perform the penetration testing. So this system delivers promising results. However, the operational cost for this system is very high because you have to run the web server, which implies a configuration of the networking services and also the databases, which is very expensive in practice. And also, the penetration test, this process is very time consuming because you have to exhaustively explore all the valid URLs to that server. Okay, if we characterize UChecker and Fuzz, we can see UChecker leverages static analysis, so the operational cost is really low, but the semantic gap between the system under test and the detection model is relatively high. On the other side, you can see Fuzz has a really high operational cost, but the semantic gap between the system and the detection model is really low. In this paper, we have presented UFuzzer. So we want UFuzzer to have really low operational cost and also very low semantic gap between the system and the detection model. So we have leveraged static analysis and fuzzing to accomplish this objective. Here we present the architecture overview of UFuzzer. We start from the PHP programs of an application, and then we perform symbolic interpretation and generate an intermediate representation defined by us that is called the heap graph. And then we instrument this graph and essentially remove those operations that depend on the networking, file system, and the database. And after that, we generate fuzzing templates from the instrumented graph. And then we have the fuzzing templates, and the last step, we perform fuzzing and identify the vulnerability. So as you can see, the first three steps are corresponding to static analysis, and the last step is fuzzing, right? Because everything is going to be run in the context of the PHP environment, so there is no syntactic or semantic gap between the PHP programs under analysis and also the fuzzing templates, essentially the detection model. And on the other side, because all the operations depending on database files and also networking are removed from the heap graph and of course from the fuzzing templates, so the fuzzing template can be run in a local and a native environment. So, okay, let's just first give some background of the heap graph. So a heap graph is a graph-based intermediate representation that models symbolic execution results of a program along all paths toward a given statement. So a node here is going to represent the evaluation result of an expression, and the edge is going to represent the operator operand and the function argument relationship. Here I'm going to give one example of the heap graph and its generation process. We accomplish this by performing symbolic interpretation. So we start from evaluating the first statement. So the first statement is going to assign a string to a variable that is called directory. So in the graph, we create a node of this string, and also we create a variable in the environment, and we make an association between them. And when we evaluate the second statement, essentially it is trying to see whether this directory is writable or not using an API that is called isWritable. So we create another node for this API that is called isWritable and make an edge between this API and the value of the directory variable. And when we evaluate this program, we know the result of isWritable is actually used as a reachability condition to all the statements inside this branch. So we create a very special variable whose name is called reachability in the environment, and make an association between this isWritable API with a reachability variable. After that, for the third statement, we start from the right side to evaluate this statement. So first we know, so this is going to be the access to this superglobal variable files. So the first dimension, we use the keyword new file to access the superglobal variable. We create array access node and make an edge between files and also this the string for the first dimension index. And also we make another array access node, and the index is going to be named. So this subtree on the left side is corresponding to the access of the original file name of the uploaded file in the file's superglobal variable. And of course, after that, we're going to concatenate the directory with the original name of the uploaded file. And this concatenate operation node is going to be created here, and the two edges are going to be created. So the first edge is connecting to the value of the directory variable, and the second edge connects to the original name of the uploaded file. And of course, this result is going to be assigned to a variable that is called fname. We create this variable in the environment and make an association between the concatenation operation and the fname variable. And after that, you can see we're going to run this move uploaded file operation, and the first argument of this API is actually the name of the temporary file. So that has been done by accessing the file's superglobal variable again. So we have done that using temp name as the index string for the second dimension. So that's why we create another array access node on the left side and create another string node temp name, and also make an edge between the access and the temp name. So we create another node that is called move uploaded file, and then we make an edge between this move uploaded file with the temporary file name, and also we make another edge destination. This edge is going to connect the move uploaded node and also the node representing the original name of the uploaded file. And then we create another special variable that is called API in the environment, and make a connection between this variable and the move uploaded file node. So the next step, we are going to perform graph refactoring. There are three objectives for this refactoring process. The first is that we are going to symbolize the super global variables because they represent the external inputs which are untrustworthy. And if applicable, we are going to symbolize the super global variables with predefined structures. For example, the file's super global variable, which comes with predefined structure. And also, we want to remove the operational dependency by symbolizing file, database, and the networking APIs or operators. And the last one is that we want to increase the efficiency by symbolizing the validation APIs. So for example, its site. So here is an example for the graph refactoring. So this is a heap graph we have generated for the example we have discussed. And using this graph refactoring mechanisms, we see there are three nodes that could be refactored, right? So you can see on the left side, this node is representing the temporary file name. So this temporary file name is derived from the super global variable files. And then the second node, the node in the middle, that is corresponding to the original name of the uploaded file. Again, that is derived from the super global variable files. And on the right side, so this is a file operation API, so it's writable, right? So in this case, according to our refactory graph refactoring mechanism, so we are going to just symbolize all these three nodes. So you can see for the first node, we're going to just create a new node to represent a symbolic value here. For the second node here, we're going to just replace that with a predefined structure for the file name. So that is a concatenation of the file name and its extension. And also for the third node is writable. So we're going to replace this node with a symbolic node. So that is called is symbolic is write. Okay, so this is going to be the instrumented graph after the refactoring process for this specific example. Next, we generate the fuzzing template from the refactored heap graph. The first step is to generate the expression of the reachability by traversing the graph, and the second step is to generate the file name of the file to be stored. And then the remaining part of this fuzzing template is invariant for all the fuzzing templates, because essentially it is trying to see is a reachability condition can be satisfied, and if that can be satisfied, we want to get the extension of the file name and evaluate whether the extension is PHP or not. If that is the case, we are going to return true, meaning that this program is vulnerable. Otherwise, it is going to return false. Of course, in order to create this fuzzing template, so we're going to identify all the free variables in the reachability expressions and also the file name expression and put them as the parameters for this fuzzing template. Here is a fuzzing template generation process following the example we have discussed. First, we're going to derive the expression for the reachability condition. We do this by evaluating the node pointed by the reachability variable in the environment. In this case, it's just a symbolic value, so we write it here as a variable that is called sym_is_write. Next step, we're going to derive the expression for the file name. We do this by number one, following the API variable and find the move upload node, and then we follow the destination edge in order to find the node corresponding to the file name of the file to be stored. So in this particular case, it is a concatenation of a string and two symbolic values. One is corresponding to the file name, another one is corresponding to the file extension. And then for these two expressions, we're going to find all the free variables included in these two expressions. Essentially, in this case, you can see we identified 4 free variables and we put them as arguments for this fuzzing template. So essentially, this is a fuzzing template we created for this particular example. With the generated fuzzing template, the fuzzing process can be done very efficiently. Essentially here, you're going to just exhaustively give different values to these parameters and see whether this fuzzing template is going to give you true as a return value. If true is returned, it means that this program is vulnerable. We have implemented our system in PHP with about 28,000 lines of code. And also we have evaluated our system using ground truth available data. So we have identified 32 vulnerability free samples, and then we have collected 27 non-vulnerable. So we tested the UChecker using the ground truth available dataset, and we compare its performance with UChecker, Fuzz, and 2 additional static analysis detection engine. One is called RIPS, another one is called WAP. So in the bottom, you can see here is the detection performance. In terms of the detection rate, so UFuzzer accomplishes similar detection rate with UChecker and RIPS, but it outperforms WAP and also Fuzz. It introduces 0 false positive rate, which is the same compared to UChecker and Fuzz, but in terms of the false positive rate, it outperforms RIPS and WAP. So another perspective we look at this system is its time consumption to perform the detection. You can see here most of the detection can be done within a few seconds, which is also the case for UChecker, RIPS, and WAP because all of them are performing static analysis. But on the other side, you can see the time consumption for Fuzz. It usually takes about a few hours to complete the detection. In addition to using ground truth available dataset to evaluate the detection performance of UFuzzer, we have applied UFuzzer to scan a large set of 9,000 WordPress plugins and also compared its performance with UChecker. So UFuzzer has detected 32 new vulnerable applications with 5 CVEs confirmed, and it detected much more vulnerable samples compared to UChecker in this experiment. So the conclusion, so we have built an improved abstract syntax tree-oriented symbolic execution engine specifically for PHP, and also we have designed a Nova system to model the server-side unrestricted file upload vulnerabilities. We have detected 32 potentially vulnerable PHP applications using UFuzzer, and we received 5 CVEs. So that's all about the introduction of our system. If you have any questions, please do not hesitate to contact me. Thank you.